What's that?
Reset our sticks.
Yeah. So I'm just giving everyone time to think a little bit more about it. All right, so Heidi's already answered. You want to give yours? What do you got? -1 raised to the n power. That's it. Okay, so let's think about why that works, right? If you plug in 1, what do you get? -1. You plug in 2, you're going to square -1 and give +1. You plug in 3, now it's going to be -1 again. Okay, this is what we call an alternating sequence. Alternating. And actually, where did it start from? It started from a negative, right? It started negative, then positive, negative, positive. So this is what we call an alternating sequence. Because it alternates in sign. Negative, positive, negative, positive, negative, positive. All right, how about this? Another important one. Wait, that's the same example? No, it's not the same example. Because it starts with +1 this time. So when you plug in 1, you have to get +1. Heidi, you look like you're ready to go, but we're going to let someone else do it. Now, I mean, this should, let's see, Martin's up. You can answer if you're okay. Yeah? Okay?
I did -1.
Okay?
Power of...
I'm going to put it right here. You said -1 to the power of n plus 1. Okay, what do y'all think? If you plug in 1 here, what are you going to get? You actually get a 2 up here. And so you're squaring that, and that gives you +1. And then when you plug in 2 into this, you get a 3, and now you're going to get a -1. So by adding that 1 to that, all that really did was kind of shifted it. Now another way to look at this would be this. This formula was the one from before, wasn't it? But this started you out at negative. You wanted to start out at positive, right? So if I just take that and multiply that by -1, wouldn't it make that positive, this negative, that positive, this negative, that positive, this negative, right? It would switch all these and create this list, right? So basically I'm saying take that formula, hit it with the -1, and you will create this formula. But this is, in fact, the same exact thing, right? Because these have the same base, so you add the powers and you get to this. So different ways you can visualize that. Okay? And we just keep going. Let's do another one. Okay, how about this one? -3, -9, 27, -81, ... It's the first time we've seen this one like this. Jonathan Salinas? Oops. Gina? I'm letting you think about it.
Something with maybe 3 to the n, but there's something with the negative.
Okay, so I think you see everything you need to see to get this. You're realizing that these are powers of 3, right? This is not jumping up by 3 each time. Like even numbers did, it jumped by 2 each time. This is not jumping by the same amount each time. But you have to recognize that all of those are powers of 3. So our formula should probably have a 3 to a power in it, right? Now before we get to that, let's talk about the alternating part of it. It's alternating, right? And it's starting out with a what? Positive? So what we can do is, before we try and figure out the 3 thing, let's just make it alternate. -1 to the n plus 1. That should alternate us, right? And that should start us out positive. right? Because that's what the previous example we did. That, throwing that into our formula should start us out with a positive number. And then the next thing we get should be negative, then positive, then negative, then positive, then negative, right? And then you're saying that the rest of it is just powers of 3. So you said 3 to the n, right? So times 3 to the n. That should work. That should work. Do y'all see there's two parts to this? 3 to the n, plug in 1, what do you get? 3. Plug in 2, what do you get? 9. 3, 27. 4, 81, right? So that's going to give you those powers, those numbers. And then this part right here is going to make it do the switching of the signs that you need it to do. Now, could you combine those together and get something else? Yes, you could. Like I could if I wanted to. You don't have to, but you could do like this. Okay, so that's just rearranging things. I peeled this apart into this, and then I put these two together because they have the same power, right? This would be just as easy, I mean, just as right, just as correct as an answer. But I think it's better for you to visualize it as, okay, I'm going to take care of the alternating part, and then I'm going to take care of the powers of 3 part. And then whatever happens after that is just algebra. This would be a completely acceptable answer. All right? So there's not a unique way to represent a sequence, is what I'm saying. There's not a unique answer. Everyone can have slightly different answers, but it better generate the same sequence. All right? Okay. How are y'all feeling about this? It's not fun anymore? Do you have any questions on it, though? Like, you understand this one? Okay. Let's try something else. Leave that one up there. How about this one? No, 4/5. It's getting there, isn't it? You want me to go back to 2, 4, 6, 8, 10?
Yes, please.
Yes? Yes, sir. You think you got it? Okay. Let's let everyone have an opportunity first before we get too far here. So you've answered one, so I'm going to come back to you if we can't get this on this first stick pull here. Octavio? I think that's Octavio, right? Ricardo? Yeah? You ready? How are you feeling about this? Okay, what is the pattern you see on the top?
Just multiplications of 2.
Yep. So that's basically 2, 4, 6, 8. That's like your even numbers. Do you know how to create the even numbers? What do you use? 2n, right? So 2n should handle the top. Now, you said you saw a pattern in the bottom too. What's the pattern you see in the bottom?
Just 5 raised to n plus 1.
Okay, so this one is like 5 to the first power. This one is like 5 squared. This one is 5 cubed, right? Right?
Yeah.
I agree with that, but if that's going to work, then it's got to follow, the pattern's got to be the same back here, so we have to look at this one as being 2 over, you need this to follow backwards. Does it?
Yes.
What do we really have here? 5 to the 0, because 5 to the 0 is 1. See, that's tricky. That's a little tricky, isn't it? Even though that was not written there, 5 to the 0 was not written, we have to understand that the pattern works backwards. Now, Ricardo, there's also an alternating part to this, wasn't there? Okay, so let's put this all together, Ricardo. I always like to start with the alternating. So give me the piece that's going to make this thing alternate the way it needs to alternate.
Negative 1 raised to the n.
to the n plus 1. Okay, everyone okay with that? That'll take care of our alternating. Now, you said the top, the numerators, were just even numbers, right? So I'm going to create a fraction here. The top you said is just 2n. All right? Now the bottom one is tricky because you need to start out where? At 0. So when you plug in 1, you need to be at 0. When you plug in 2, you need to be at 1. And when you plug in 3, you need to be at 2. And when you plug in 4, you need to be at 3, right? So what am I going to put here? 5 raised to the n minus 1. So if I plug 1 in for n, I'm at 0. If I plug in 2, I'm at 1. If I plug in 3, I'm at 2, right? That should generate that sequence. Yeah, so can you kind of see what I mean? It's like kind of a light bulb sort of thing. Like when you get it, you start to be able to piece these together. But if you have trouble, and this is not something that's easy to teach. This is not like, you know, integration by parts. We're going to do ultraviolet minus voodoo every single time, you know. That was hard enough, but this really is hard to teach. Like I can't really teach you how to see it. I mean, I can try, but some people see it, some people don't. Okay. Ooh, I've got a good one. You know what? Let's make that -1. Okay, I'm just thinking here. That's it. Okay, I don't anticipate that. I'd be surprised if somebody gets this one. I'd be surprised. But I'm showing it to you for exactly the reason that I want you to be aware of a certain thing. And once you see it, then now you know, all right?
There's a multiple of 3, so like each one, like 6, 24, and 120 can all have a common factor of 3.
Mm-hmm. But the 2 doesn't work that way though. And you got to, whatever your formula is, needs to account for everything. Like it's got to go all the way back to the beginning. So when I plug in 1, I need to get this. When I plug in 2, I need to get this. When I plug in 3, I need to get that, right? Okay, so here, let me, Tatum's not here. Corey, we've got you already, right? Steven, what's that?
I see the n plus 1 at the bottom.
Okay. Steven? Yeah. I mean, I'm putting you out on a limb here with this one. But tell me what part of it you know you could take care of, like the alternating part, right? The alternating part can be handled. So what would that formula be to get us to alternating? So n or n plus 1?
Oh, just n.
Just n. So just always to check, just think about if you plug 1 in, you're going to get negative, right? So that's what you want.
Yeah.
And instead of memorizing, no, it's going to be -1 to a power, and just think about that first step, what it would be. Okay, yeah. What about all the numerators, Stephen? I mean, forget the negatives. What are all the numerators?
You got an over 1, and then probably it's going to be an over -1.
No, I'm saying numerator-wise. At the top, this is just a 1, 1, 1, 1, 1. So it looks like the pattern is 1 on top. This may be wrong, but, right? It looks like perhaps we just have 1 on top the whole time. Yeah? And now it's those bottoms. See, the bottom is not, they're not jumping up by the same amount each time, right? So it's not like 2n or something like that, or 5n. And they're not exponents, like 3 to the n, right? Like 3 squared, 3 cubed. So they're not exponents, they're not jumping by a common factor, but it is something. So let's see if anyone has ever seen this before. This is 1 times 2. This is 1 times 2 times 3. This is 1 times 2 times 3 times 4. This is 1 times 2 times 3 times 4 times 5. Have you all seen that before?
Yeah.
Okay, so some of you have, some of you haven't. It's called factorial, and it's something that I need to do on the side to make sure everyone is clear with. Okay, we have a special notation in math, or special, yeah, it's notation. It's this thing called factorial. It's used a lot in statistics, the factorial. And what it is you write a number like, it has to be an integer, it has to be positive. If I write the number 7 factorial, I write 7 with an exclamation point after it. That is a mathematical symbol, and what it's telling you is to do the following multiplication. 7 times 6 times 5 times 4 times 3 times 2 times 1. You don't actually need the 1, but I like to go all the way down to 1 anyway. All right? So if you were to get on your calculator, do 7 times 6 times 5, and then whatever that number is, that's 7 factorial. All right? So in general, n factorial means n times the number 1 less than that. Right? So if it's 7 factorial, it would be 7 times 7 minus 1 is 6. And then you'd subtract again. So it'd be 7 minus 2, which would be 5. And you keep doing this, n minus 3. You just keep on taking 1 away until you get down to 1, right? That's the definition of n factorial right here. But n has to be a positive integer. So n has to be an integer, but it can also be 0, right? So we can just, there's different ways you can do this. You could say greater than 0 up here. Sorry, greater than or equal to 0. That would tell you that you're an integer greater than or equal to 0, which means you could be 0, 1, 2, 3, 4. All right, so that's the first thing we have to understand is that those are factorials. So what factorial is this right here? 5 factorial. This one is 4 factorial. This one is 3 factorial. This one is 2 factorial. And this we have to look at as a fraction, right? 1 over 1, and that's 1 factorial. But this thing the pattern has to go all the way back. And so if it's going to work, this last one has to be what, according to the pattern? 0 factorial. And do you all know what 0 factorial is? It's 1. So it's crazy. Okay, so 0 factorial is a very special factorial. It is defined to be 1. All right? So I'm going to add that to this over here. 0 factorial, by definition, and when we do something in math by definition, that means we are defining it. We put a colon in front of an equal sign. And that tells everyone we're defining 0 factorial to be 1. So most logical people would think 0 factorial is 0 because of the definition. But 0 factorial is actually 1. Has anyone heard of those prizes they have for math problems? Those $1 million prizes? There's one called the Riemann Hypothesis. Has anyone heard of that? Okay, well, it's an unsolved problem that if someone could solve it, basically you'd be a millionaire. They give you $1 million. There's a few of them. There's like 10 problems or so that they have out there. But the Riemann Hypothesis is the one that has eluded mathematicians for a long time. And it has actually a lot to do with this factorial function. You can actually define factorials for things that are not integers. Like you could do like 1/2 factorial, which is really strange to think about, but we're not going to get into that. But once you can kind of wrap your head around the idea that this can be extended to non-integers, like real numbers, then things get really weird. And there's this one problem that we've been trying to figure out for a long time. It was proposed by Riemann. Remember we did Riemann sums, trying to add up all the rectangles? Those were called Riemann sums. That mathematician, he has a conjecture about it. Okay. What happened? Oh, so back here. All right, so this is a factorial down here, isn't it? What factorial is it, though? Because I need to start out at 0 factorial. N minus 1. N minus 1 that quantity factorial. So the negative 1 to the n gives us the alternating. 1 is always on top. These were factorials on the bottom. We got to start at 0, right? What do y'all think?
Where does the negative 1 come from?
Because you have to start at 0. You have to start at 0 factorial. All right, maybe one more? Okay. How about this one? Hold on, I might need my calculator for this one. I know that's not fair to you, but... This one's not even going to alternate. Mm-hmm. Okay, there you go. It's good enough. So maybe you look at that for a while and you try and figure out a pattern. Anybody? This is another one where I wouldn't expect you to see it. It has nothing to do with factorials, though. I'll tell you that much. What do you got?
N to the n?
Yes! Good job. N to the n. How'd you get that?
Looked at it.
You just looked at it. That's exactly right. That is the answer.
1 to the 1 is 1, 2 to the 2 is 4, 3 to the 3 is 27.
3 to the 3 is 27. 4 to the 4 is 256. I mean, yeah. That's n to the n. That's n to the n. Okay. So we have a way of generating even numbers and odd numbers. We can alternate things. We know sometimes we've got powers in there, like 3 to the n. We've got factorial sometimes. Maybe we could even have this, right? So this is all just a general feel of what sequences are, all right? Give you a little more notation, okay? We have some time still. Some notation. So we've already established this idea that, you know, like for example, if we were to take n to the n, that example right there, we all understand this notation that defines a sequence, right? That defines a sequence. Now we could use an alternate notation to define the same sequence. We could use this, and then it would be understood that that is that, okay? N to the n, in a set of braces like that, is this. So these are all equivalent, basically, is what I'm saying. Now, what if I do this? You tell me what you think this is. So that notation is being very explicit about where they want you to start and where they want you to stop. Now, I've told you we're always going to start at 1 and end at infinity, right? Like never end for an infinite sequence, right? An infinite sequence would always start at 1 and end at infinity, right? That's the way we started class, but I'm here to tell you we're not always going to start at 1, all right? So we need a notation for starting somewhere other than 1. So let's say I wanted to start this sequence here at 27, right? And then go on forever. Then what I would do is I would write this and then put what here? 3 to infinity, right? 3 because my third one is the 27. Okay, so that notation just gives you like a starting and an ending. What if I did this? That's a 2 and a 4. That's a finite sequence now, right? Now you're looking at a finite sequence. Start at 2, go 2, then 3, and then 4 and stop. So they're kind of like the limits of integration, but they're more like when you use sigma notation, they're more like the lower index and upper index of a sigma notation than they are of an integral. Okay, so that's just some notation. All right. All right, let's keep going. I forgot my book and my notes, and I didn't know if we were doing this today, so I'm winging it. What's that?
My Kindle book if you
No, it's okay. It's okay. I should know this well enough by now, I think. I'm just trying to remember the order of things. Let's talk about increasing sequences. So we're out of notation, okay? That's just notation right there. Increasing sequences. What do you think an increasing sequence is? What's that? What do you mean goes up?
Like, it's kind of like adding a fixed number every time.
So as you move through the sequence, the numbers get bigger. That's it. Okay, that's an increasing sequence. So given a sequence, gosh, given a sequence, we will say it is increasing if a sub n is less than a sub n plus 1. Do y'all know what that means? Upside down capital A? For all. For all n. So this is the definition of what it means to be an increasing sequence. So whatever, it's like, you know how we said a sequence is just like a sub 1, a sub 2, a sub 3, a sub 4, right? Whatever your sequence is, this one's the first one, the next one's the second one, that's the third one, right? Then your fourth one. To be increasing means that if you pick the nth one, let's say you pick the third one, right? Then that third one must be smaller than the fourth one, right? As long as you maintain that the whole time, then this thing is increasing. So the numbers are getting bigger as you go, right? That's an increasing sequence. What does decreasing mean? Same definition, flip the inequality over. So they get smaller as you go. So decreasing sequence. For all n. I'm shortening things up so I don't have to write all these words down. But given a sequence, we will say it is decreasing if that inequality flipped over holds all the time. All right? All right, next definition, a monotonic sequence. Monotonic. If a sequence is increasing or decreasing, it is called monotonic. So monotonic is more general. If I tell you, hey, I've got this sequence and it's monotonic, it's either increasing or decreasing, okay? Right? It's either increasing or decreasing, but it doesn't specify. So monotonic is kind of a vague description, but it tells you that it's one or the other. Are there sequences that are not monotonic? Yeah, we looked at like the 1, 1, -1, 1, -1, right? 1, -1. That one just keeps switching. It never follows a pattern of this inequality working or the other one. All right. Another definition.
it just stays the same the whole time? Would it have to be increasing?
It depends on how I've seen books define sequences different ways in terms of increasing and decreasing. Who has the book? Let me grab it. You know, on my inequality, I had strictly less than or strictly greater than on increasing and decreasing. I'm going to look right here because I forget if this book includes the... And then I'll answer your question. Whoa. No. Yeah, it's a strict inequality, so there's no equivalence. So monotonic has to be one or the other. So flat line would not
So if I had a sequence that was increased but every once in a while had like a flat spot, it wouldn't count as
would not count. Thank you. Would not count. Yeah. Now you could say it's monotonic on a certain piece,
Yeah.
but you couldn't say it's monotonic all the time. Yes.
When you say monotonic, is it like when you have a sequence that say it starts at 2 and then jumps down to like -7 and then comes back over to +5? Then
Can't.
Comes back to like
Then it wouldn't be monotonic.
Okay, so
Monotonic means you're either increasing or decreasing. So an increasing sequence looks like this. Right? That's an increasing sequence. Remember, sequences are dots when we graph them. So an increasing sequence is going to look like that. A decreasing sequence would go the other way. Right? But it's one or the other, not both. It can't be both at the same time. Okay, so now the next definition is bounded. Okay, a sequence is said to be bounded above if there exists a capital M. So that means there exists there exists a capital M such that, what do you think I'm going to say right now?
Never reach out.
You never reach it. That capital M is always bigger than your sequence, all the time. Such that A sub n is greater than, is less than or equal to capital M for all little n. Okay, a sequence is said to be bounded above. Think of it bounded above to mean like the ceiling, okay? To say that our sequence is bounded above means that there's some number, there exists some number m, such that that number is bigger than every single number in my sequence for every single number in the sequence, right? So when I draw a picture, you know, let's say I have a sequence that does this. That like just goes back and forth. Then right there, there's a capital M. This sequence is bounded above because there's a number that's always bigger than anything in the sequence. And now if I change that to bounded below, what are you going to do? It's now you have something that's smaller, right, than everything. So bounded below. So bounded below means that there exists a little m such that A sub n is bigger than or equal to little m for all n. So there's some number underneath your sequence. I'm going to steal Heidi's book again. No, it's all right. Just leave it right there. Bound. Yeah. All right. Last little definition. Last little definition. So do y'all understand bounded above? There's like a ceiling. Bounded below means there's like a floor, and your sequence is always between those two. All right? So now, what about if you just say a sequence is bounded? A sequence is said to be bounded if, okay, so tell me what you think. I told you what bounded above meant. I told you what bounded below meant. If I just tell you that I have a sequence that's bounded, what do you think that means? Ceiling and a floor? Or ceiling or a floor? What do y'all think? To say a sequence is bounded, do you think that means that it has to be like ceiling and floor, or one or the other? Yeah, this is a little subjective, but the textbook says bounded means you have a ceiling and a floor. Okay? So a sequence is said to be bounded if it is both bounded above and below. That means you have a ceiling and a floor. If you have both a ceiling and a floor, then you are bounded. If you have a ceiling and you don't have a floor, you can just say you're bounded above. If you have a floor but you don't have a ceiling, then you can just say you're bounded below. But to say you're bounded is a very strong condition. It's giving you a top and a bottom restriction. Okay? And I'm going to stop with just the final theorem, or this is the first theorem of the section, but this is kind of the result. We'll work with this next time. It's the bounded monotonic sequence theorem. And here's what it says. Every bounded monotonic sequence converges. Now, we haven't even talked about the word converges yet. We haven't even discussed it, and we will do that next class. But I want us to just consider what this theorem might be saying. Think about the sequence we had that was -1, 1, -1, 1, -1, 1, right? If I were to look at that graphically, it does this: -1, 1, -1, 1, -1, 1, -1, 1. Is this sequence bounded? Yes, it's bounded above and below. All right, is it monotonic? It's not monotonic. It doesn't go up, right, and keep going up, or it doesn't go down and keep going down, right? This theorem says if you have both bounded and monotonic, then it must converge to something. Your sequence must head to something, kind of like a limit of a function. Remember when we took limits as x went to infinity and a function was kind of like finding the horizontal asymptote? This is basically saying that if you're bounded and you're monotonic, you have to go to a certain place. So let me give you an example of a function that does that, or a sequence. Look at the sequence a sub n equals 1 over n. Very simple sequence. If you look at that sequence and you were to write it out, it would be 1, 1/2, 1/3, 1/4, right? 1/5, ... right? Get smaller and smaller and smaller as you go. That is definitely monotonic, right? It's every time you go, the next one's smaller than the one before. So this is monotonic decreasing, right? You got a monotonic, so we got monotonic. Is it bounded? So is there a number that's always above? Everything in here is always below something. Let's see. So we plug in 1, we get 1, and then 1/2, 1/3, right? So what's happening? So can you think of a number that's above all those?
We're just starting at 1 and going forward.
Yes, because it's a sequence. We're starting at 1, yes. So how about 2? 2 is a number that's bigger than all of those, right? So it's bounded above. Is it bounded below? Yeah, it never gets to 0, right? All those, I mean, it heads towards 0, but it never gets there. So you could use -1 as a lower bound. So you have a bounded sequence, and it's monotonic. It has to head somewhere. Where's it heading? It's heading towards 0, right? These numbers are headed towards 0. We'll pick up with that next class. There's really not a lot of homework for this. Heidi, can I look at your book real quick again? What I would say for this section right now for 8.1, some good, I guess the things you can look at that would be worth your time are numbers 5, 6, 7, 8. That's it. 5, 6, 7, 8. They give you 4 sequences like I did on the board, and they ask you to come up with a formula. It's page 434, section 8.1.
What about all the rest?
Don't do those yet. We haven't talked about it yet. So what we'll do is we'll start next class. We'll still be in 8.1, and we're going to be talking about limits, the limit of a sequence. Just like we did limits of functions, we're going to do limits of sequences. All right. Enjoy your weekend. Stay out of trouble. Are the Astros losing tonight? What's happening tonight? They're winning tonight? Yeah, let me turn my camera off real quick.
Create